Data structures for database design. Data structures are the backbone of efficient database design, enabling developers to organize data in ways that optimize storage, retrieval, and manipulation. Whether building relational databases or handling unstructured data, choosing the right structure can significantly impact performance and scalability. In today's data-driven world, understanding how to implement appropriate data structures is crucial for creating robust systems that handle vast amounts of information seamlessly. This guide explores key concepts that every programmer must know when designing modern databases. The role of data structures in modern databases. Data structures provide a framework for organizing information within databases, ensuring fast access times even as datasets grow exponentially. They determine how queries will be executed under various conditions. From hash tables facilitating rapid lookups to B-trees managing disk-based indexing efficiently, each structure has its place depending on usage patterns. Understanding these differences helps architects make informed decisions during schema design phases. Hash tables, ideal for scenarios requiring constant time complexity for insertions and searches by using key-value pairs. B-trees, optimized for storing sorted data while maintaining logarithmic time complexity for search operations across large volumes. Selecting appropriate indexing strategies. Indexing strategies play a critical role in determining query response times. Choosing between clustered versus non-clustered indexes involves careful consideration of data distribution characteristics. A clustered index organizes table rows physically according to indexed columns, whereas non-clustered indexes store pointers separately from actual row locations. Both approaches have trade-offs based on specific application needs. For example, in transactional applications where frequent updates occur alongside range queries, composite indexes combining primary keys with frequently accessed attributes often yield optimal results. Evaluating cardinality ratios between columns also guides decision-making processes regarding which fields warrant indexing treatment. Understanding tree-based storage mechanisms. Tree-based structures form the foundation of many advanced indexing techniques used in contemporary DBMS implementations. These include but aren't limited to B+ trees and interval trees. B+ trees excel at supporting high concurrency environments due to their ability to maintain balanced height through dynamic node splitting mechanisms. Their leaf nodes contain actual records rather than pointers, reducing I/O overhead substantially. Interval trees facilitate spatial queries effectively by partitioning ranges into hierarchical layers, making them particularly useful for Geographic Information System (GIS) applications involving location-based searches. When implementing tree-based solutions, factors such as fan-out ratios and page sizes influence overall efficiency levels significantly. Optimizing memory usage through efficient structuring. Memory optimization becomes increasingly vital as datasets expand beyond available RAM capacities. Techniques like compression algorithms combined with smart structuring methods help mitigate resource constraints. Data normalization practices reduce redundancy by decomposing complex entities into simpler forms without losing essential relationships. However, excessive decomposition might lead to increased join operations affecting performance negatively. Different encoding schemes offer varying degrees of space savings. Delta encoding works well for numerical sequences showing gradual changes over time frames. Choosing between dense versus sparse representations depends largely upon expected access patterns and frequency distributions inherent within particular domains. Handling unstructured data challenges. Unstructured data presents unique challenges since traditional relational models struggle to accommodate irregular formats. Implementing document-oriented stores provides flexible alternatives better suited for JSON/XML payloads. NoSQL solutions like MongoDB leverage embedded documents capabilities, allowing rich querying semantics similar to SQL dialects, albeit structured differently underneath. Schema validation ensures consistency despite flexibility offered. Graph databases represent another paradigm shift suitable for modeling interconnected entities naturally found in social networks, recommendation engines, etc. Using adjacency lists coupled with traversal optimizations enhances navigation speeds considerably. Time series databases specialize in temporal analytics requirements through optimized append-only architectures, minimizing random write amplification issues commonly encountered elsewhere. Evolving trends in contemporary data architecture. The landscape continues evolving rapidly, driven primarily by cloud-native computing paradigms, shifting away from monolithic deployments towards microservices-oriented infrastructure designs. Serverless architectures introduce new considerations around state management, given ephemeral nature associated with function invocations, limiting reliance on persistent local caches. Cold start problems related to machine learning pipelines necessitate innovative caching layer integrations capable of serving pre-computed summaries quickly whenever required. Edge computing introduces additional complexities, requiring lightweight versions of classical data constructs adapted specifically for low-latency processing closer to end devices. Best practices for scalable system development. Adopting scalable development methodologies requires proactive planning stages, incorporating load testing simulations early enough before full deployment cycles commence. Implementing sharding strategies distributes workload evenly across horizontally scaled clusters, preventing single points of failure situations emerging unexpectedly later down the line. Replication protocols ensure fault tolerance by maintaining redundant copies residing independently yet synchronously updated simultaneously wherever necessary. Monitoring tools integrated continuously track metrics, providing real-time visibility into potential bottlenecks forming dynamically amidst changing workloads. Common pitfalls to avoid during implementation phases. Failing to analyze access patterns thoroughly leads to suboptimal choices, resulting in either unnecessary overhead costs or poor performance outcomes later on. Misjudging size estimations for growing collections may cause premature capacity limitations, forcing costly migrations once thresholds get exceeded. Lack of version control mechanisms increases risks substantially, especially when dealing with multi-user collaborative environments needing atomic update guarantees consistently applied everywhere involved. Ignoring security implications opens vulnerabilities, exposing sensitive information, potentially leading catastrophic breaches impacting business continuity permanently thereafter. Conclusion: data structures remain central components influencing everything from basic CRUD operations up through sophisticated analytical workflows prevalent nowadays. To build resilient, future-proof systems capable of adapting gracefully against ever-changing demands, mastering underlying principles governing effective organization remains indispensable knowledge worth acquiring diligently now.